Use it heavy.
Exactly.
Rest of you guys, if you weren't there Saturday, you better be there Wednesday, right?
Wait,
Oh.
Both girls and guys are playing Wednesday, 6 and 7:30. I'll be there. You guys have no excuse this time.
Wait, I do. Seattle.
It's gonna be a test day. No homework. See, look, I worked it out. 6 and 7:30. Come to both. Because they're both in state.
Yeah. I mean, I'm sorry.
Alright. No, but by being in the open division, they're able to play.
Coming
right?
here.
Yeah, when you go to open division, you automatically get a spot in state, because open division is the top team in their state.
Yeah.
And so it's like,
Who gets tracking? Alright, cool kids, we're recording, so let's go ahead and focus on it on the honors pre-calc. You guys got too used to me sitting behind, now you won't pay attention to what's in front of you. Alright. You might not stay in front of you, but I'll be here for a little bit. Question, what did you guys do to check using the yellow box? Then we'll listen to Luke this way.
You do like the crisscrossy.
Oh, but the very first thing we had to do is plug it in, right?
Yes.
So we had to plug in, what did you guys do first?
Negative 2,
We did that one.
Yes.
Bless you. Then a 1 and a 1 and a 1.
Yeah.
Solid.
Now, there is technically a little, you can think about the plus or minus 1/2, but kiddos, what happens when we go to solving this? What happens to him? Does he really matter? No, because he'll multiply to the other side and just be a 0. Anyways, so we're just trying to ask, hey, is this a 0? True? What row did you use, or what column? The middle one? Sounds good to me. So, when we use the middle, we did a quick review of determinants of a 3x3, right? Okay, so if we're using the middle one, then think about cross, who's left? Wait a minute, is there a plus or a minus in front of that one?
Minus.
Because, right? Positive, negative, so that has a minus. Then we're going to have a plus with another one, that's nice. Cross, who's left? Is it working?
Yeah.
Then don't we have a minus? Hold on. Oh, I stole a 7 without meaning to. There we go. One last one. Cross with the last one. They have the minus because of the sign with the positive, negative, positive, negative. So we end up with -2, -2, 7, 5, right?
Yes.
Now how do we proceed?
Main minus.
Mean minus opposite. Mean opposite? It's not a thing anymore?
Opposite.
Oh, it's not a thing anymore. Okay. We have -2 minus 5. Did you guys get minus -7? Then we have -2 minus 7. Did you get -9? Then -10 plus 14. Yeah?
So it's plus. No, right.
Is that good? Double check them. -10 minus -14 is -10 plus 14. But there's a minus on the outside. That all adds up to be, well, that's a positive. 7 plus -9. 7 minus 13, I'm pretty sure that's not so much a good 0 number, right? So therefore we can say false. To what? Question, are they collinear? Yeah? Now, Luca, hold on. What did you see with the points that you were able to figure out?
I saw the slope. Like they're 2, 2, 1, 1, and then it should have been either 7, 7 or 5, 5.
Yeah, if it was on the same line, he was able to think about the slope because the slope should be the exact same as well in order to make them parallel. Although, I guess it'd be a part, oops, I moved it. It'd be a part of one nice line. So you think about the slope just being the same. Okay, either way, are they collinear? And the answer is no. Question, what are we doing in section 8.5? What are we looking at applications of?
O's.
Matrices and determinants.
Yeah, determinants of matrices. We started off with how to use Cramer's rule. That page we basically did on the page before, so we forgot that. This one was, why did I forget this example? Wasn't he a good example? Anybody remember? How would we set up Kramer's rule? Yeah, it's gonna take forever because we'd have x equals, and wouldn't he have like his own set of a determinant of a 3 by 3 over a determinant of a 3 by 3, and then when we have to go again for y equals, and then go again for z equals, and we were like, not about that life. Not that we couldn't do it, but I decided for us to practice determinant of a 3 by 3 using area of a triangle first of all, and then collinear points second of all. Okay, we already did that one too. Check. Anyway, I forget what pages I have. Try that one out for size. Try this example out for size. Use a determinant to find an equation of a tangent line. Oh, not sorry. I'm in calculus for a second. Lo siento. Find an equation of a line passing through the points. How on earth are we supposed to do something like that?
Well, you have x1 and y1, x0, and y2. Well, you have a matrix.
Now, granted, we could just use the old-fashioned things, right? Y minus y1 equals m times x minus x1. M is equal to rise over run y2 minus y1 over x2 minus x1. We've done that. But
Is y 0?
why is there a determinant? Not necessarily. Maybe, maybe not. What do we know, though? 3 points on the same 3 points. 3 points on the same line would be collinear. True?
Oh, so y equals 7.
Three points would be collinear. Now, Luke has already figured out and said, hey, wait, I know what the answer is because if we did the formula for slope, the slope is 0. Another way of looking at it, y must be 7. However, that is the equation of the line. How can we use a determinant to find that, though? What am I doing? What am I setting up? Yeah, the area of the triangle, well, they're all on the same line. Oh, yeah, that's right, collinear. It's just going to be 0. So, hey, couldn't we use the third column of ones? That's nice. We can always use that with area of a triangle and or collinear points. So let me go ahead and start this puppy out. So we have, let's see, positive, negative. This is going to be a plus and a minus and a plus, right?
Mm-hmm.
Okay. So we have positive 1, cross cross. Negative 2, 7, xy. You guys good? Then we have a minus 1. Now you guys fill in. Prove to me that you're tracking. I've done that guy. Come on to the next guy. 10, 7. Sounds good. 10, 7 and what? Got it. Prove to me you're still tracking. Find me the last one. 10, 7, yeah. Good, 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 good. Wait, and then we set the whole thing equal to 0. Focus. I distracted ones in the front. So main minus opposite. Don't we have, let's see, negative 2, oops, no, negative 2y, yeah? Minus 7x minus 10y minus 7x plus 70 minus negative 14, which will be plus 14. Look good? Why did I put parentheses around the middle determinant, but not around the other two? Yeah, there's negative 1 in front. I have to distribute. The other ones have a positive 1. No big deal. So I end up with negative 2y minus 7x minus 10y plus 7x plus 84 equals 0. What's going on with my x terms?
You can cut them.
They cancel out.
What'd you say?
It's negative, Ms. D, it's negative 84.
Yeah, it would be negative 84 because you had to.
Nice.
Negative 12y.
Good. Subtract the 84 and y is equal to 7, and isn't that what we hypothesized at the beginning? Now, some of you knew why we hypothesized, some of you didn't. So in order for 2 points to be on the same line, if their y's are the same, it must be a horizontal line with different x values. Dun, 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 dun. Nice. So it's just showing how you can actually use these applications different ways. Alright, you tracking? Tracking, lacking, not like a tracking? Like a tracking's not good. Here we go. Write it once. Write it once and then use it. P.S. on the test. On Wednesday, before choir leaves, we'll fit it in. And before the girls and guys basketball games that you can all go support because you don't have pre-cal. I will give you this written out. I'll probably just like project it on the board. I'll also have like a bigger copy of it and I'll just put it on the board during the test. Sound good? But for your notes to be able to use for homework and in notes, believe me, it will simplify your life to have it written out once.
Wait, is it 0? Like just a blank?
0 is a space. 0 is a space. Now, just one of the most basic ciphers. Ciphers. One of the most basic way of encoding what you see right now. If you write A is 1, B is 2, C is 3, D is 4. Now, if you notice, I kind of put 2 pieces together, so you notice how I go from 4 to 5 to 6 to 7. If you guys want to go straight down, you can. I had put 2 pieces together, and that's why it's kind of awkward. See?
It doesn't know what to do for it.
Yeah, I got like copy and pasted 2 together. They didn't fit side by side so well. Substitute. You can just write them whatever way you want, whatever's faster or easier for you to see. So A is 1, B is 2, C is 3, D is 4, E is 5, F is 6, etc., etc., etc. The points of ciphers, the points of codes, well, there's all sorts of different points. All sorts of different purposes. World War I, World War II. Have you guys ever seen, oh, why did it just fly out of my head? Benedict Cumberbatch. Thank you. Thank you, thank you. Trying to break the code. Now that was quite complicated. They were using the early computing machine in order to help them out. So there are complicated ways of enciphering. There are simple ways of enciphering. Just because you see numbers does not necessarily mean that A is 1 and B is 2 and C is 3, right? For instance, how could you make this just a little bit more complicated if you were going to, like, I don't know, do some sort of coded message to a friend? Do what? Yeah, maybe. Make 26A, 25B, 24C. That's one way. Keep going. What's another way? Maybe. A is 1, B is 3, C is 5. Could have fun that way. What else? Switch the odds and the evens.
So like 1 would be that little score, and then 2 would be A. Score. Or you screw it up.
Oh, you can, yeah. That's called a shift cipher, what Brandon just said. A shift cipher is 1 second, maybe A is 1, B is 2, C is 3. The next second, maybe 0 is A. Maybe 5 is A, 6 is B, 7 is C, etc. That's just a basic shift cipher. In college, I had, it was actually a math elective called cryptography. And we had to design and or produce some sort of enciphering encoding machine. Could be a machine, could be, I actually ended up, I was playing with wood and ended up having like a circular shift cipher, so where you could have all the letters of the alphabet and all the numbers, and you could like shift it to wherever you want it to be. So you could make a 1 second, the next second you can make a 5, and then make a 22, and then anyway. It was pretty nifty. The person just needs to know where to start from, right? But if they don't know where to start from, they need to know different things like, what's some of the most repeated letters in most messages? Maybe the vowels. Consonants, maybe like S, right? So if it was a simple cipher where wherever you were, things weren't moving or changing in the sense of if A is 5, then B is 6, and C is 7, etc. Then if you see repeated or commonly repeated letters, and you could maybe attach them to try E, try S, try A, try, what's another repeated letter? Maybe the rest of the vowels, maybe R. So there are ways to break shift ciphers actually quite simply, quite quickly. So one way of making this a bit more complicated is to not make it just a simple shift cipher, but like what you guys were saying with the evens and the odds, try to incorporate something a little bit more complicated, or like the skipping, that makes it a little bit more complicated. However, as you notice, once again, there are very brilliant people that could break those ciphers fairly quickly. All they need to do is figure out some of the repeated letters or some of the repeated patterns. They see numbers in their head. So then a way to make it more complicated is a cipher, something that encodes a cipher that is always changing. That kind of comes into imitation game just a little bit. I think imitation game, they kind of made it more of an agenda movie at the end, but it was still very interesting and the history was mostly accurate. So it might be worth your while to see. However, with computers came the ability to have codes or have ciphers that are continually changing. And if you guys try to buy things online, like with Amazon or doing sort of online banking, maybe you've seen before maybe you've seen things like 16-bit encryption. Once you get a credit card and start entering numbers and stuff that they talk about. I have no idea. Upstairs? Mr. Strick's room? Where's room 220? 220? Senior dining?
No,
It's upstairs. It's upstairs by the Mr. Hart's room.
Oh, like
Yeah.
foreign language rooms? Somewhere up there. But another way to encode and make it a bit more complicated is using matrices, which is kind of fun.
So this part might be fun.
Maybe. However, in order to decode anything, there has to be a key. There has to be a key to breaking the code. For a shift cipher, the key is knowing what letter is A, right? The key would be A is 20, A is 17, A is 3, A is etc. That'd be the key for the shift cipher. For a encoded message that has been encoded with matrices, the inverse matrix of an original is going to be our key. So long story short, matrix multiplication is going to allow us to encode messages. You guys will definitely want your calculators. You are not going to be doing this work by hand. So if you notice, these numbers get huge. So the steps, right? Uncoded row matrices. Now uncoded means, basically, associate letters with numbers. Now once again, we do know that we can make this even a little bit harder if we did have A equaling 1, but we're going to make it super mixed up with a matrix anyway. And if you think about matrix multiplication, you're doing all sorts of different operations every time you do matrix multiplication. So being able to break that would be pretty complicated. And you'll see what I mean in a second. Write uncoded row matrices of n order, associating the letters with numbers but not doing anything with those numbers. Make a matrix out of them. Number 2, encode. What does that mean? Put it into code, yeah. Put it into code. Encode it by multiplying by an invertible matrix of n by n order. So here is one limitation of our cipher. We need to, maybe I won't put it in parentheses, it needs to be invertible and it needs to be a square matrix. Now to be invertible, remember what needs to happen? The determinant of A cannot equal 0. If you choose a matrix to encode your message whose determinant is 0, there's no way to decode your message, which would be a bummer. So encode by multiplying by an invertible matrix of n by n order, so it needs to be an invertible matrix, hence not non-singular, hence the determinant cannot be 0. And then, how could the person on the other side decode, get it out of code, right? Get it back to the original numbers and then be able to go to letters? How do you undo matrix multiplication? Divide. No. Multiply by the inverse. So you can encode with an invertible matrix. You can decode by its inverse. So, given an encoded matrix and given the original matrix used to encode it, finding the inverse matrix, you can multiply by the message and get back to the original content. So let's go ahead and see how this works. You guys ready? Here is a message. Okay? Now I've done a full example, like all the way written out the entire way to encode it number 1 and then decode it, go back to the original number 2. So let's say we wanted to hide the message, meet me Monday. Let's say we wanted to hide the message, meet me Monday. The very, very, very first step is to get the letters into numbers. We can't make a matrix out of letters. That's not going to be very helpful for us to do anything with. So if we decide to use, check it down here, we're going to use letter A as our key. He's going to be the matrix that we're going to use, some random matrix that, believe me, this determinant is not 0, so he has an inverse. We're going to use matrix A to encode the message. We're going to use matrix A to encode the message. Now, what size is matrix A? He's a 3 by 3. So if he's a 3 by 3, we need to go ahead and, knowing the properties of matrix multiplication, we need to split up our message. Wait, what message? Oh, M goes with, guys, look at your little diagram. Is M 13?
Yeah.
Is E 5?
Yeah.
Yep, E is 5. Do you guys see what I mean by repeated letters? Somebody who's trying to break this code, like if it was just A is 1, B is 2, C is 3, well, number 1, they'd try that first. And number 2, they'd see, hey, there's lots of 5s, I bet that's E. And guess what? They end up being right. So anyway, coming back. So you assign each of the letters. Now wait a minute, hold on. What did I miss? M is not 0. Who is 0? The space, right? Then M, then E, then the space, then M, etc. Okay, so once you translate or change the letters into numbers, then because we're using a 3 by 3, we need to go ahead and group these letters by 3s. Group these, I should say numbers, because now they've been changed into numbers. Group the numbers by 3. Now if you guys noticed, Y is 25. So why is there an extra number? We have to complete, we have to complete the set of 3. We can have as many sets of 3 as we want, but if the message does end, we need to go ahead and complete the set of 3, or else we're going to have an impossible message to encode. Now, how do we encode? We have our invertible matrix A. We have the key that we're going to multiply our matrix by. Wait, what matrix? Our original one. 13, 5, 5. Wait a minute. How do we make this matrix? We make a matrix B. And who are we going to put in matrix B? Everybody. So what size is matrix B gonna be?
5/3.
You see it? We can have as many rows as we want when it ends with 1, then 25, then 0. We can have as many rows as we want, but to be able to do matrix multiplication, I need to make sure that I have a 3 as the number of columns. Technically, I think n is rows, so I'll make it a 3 by n. In this case, though, since we can see our message 1, 2, 3, 4, 5, we end up having a 3 by 5. What's the only way that we can legally multiply if our encoding matrix is a 3 by 3 and if B is going to be at least 3 by somebody? It depends on how long our message is. Yeah. Not B times A though. Remember, don't we need the insides to match? So why do A times B? Yeah, however long the message is, as long as I do A first, I'm going to be fine. So take your message and you multiply your key or your encoding matrix times your message. So if you guys want to write yourselves a little note. You do the encoding message, which sometimes could be given to you. Technically, you guys could make that up if you were doing your own. The reason why the book chose one for you is otherwise there'd be no way for us to check as to whether or not you're right unless we were to collect all of your different keys and check all of your different keys with all of your different inverses. That would take forever. So we have you using one set encoding matrix. Now, look at the beginning letters. Ready? Look at the beginning letters. If you were to just give someone that string of letters, remember how I said it might be pretty easy to crack? Number one, the first thing most people try when they say C numbers, and they know it's the message, is, hey, A is 1, B is 2, C is 3. But remember, I also said even if it was a shift cipher that some of you guys talked about, if we saw repeated letters, we would assume those were E's and then see if we're right. And then go through other repeats like S's or R's or A's. Especially if they're next to each other, think of words that might have more than one letter. Anyway, it can get broken pretty quickly or cracked pretty quickly. But look at this matrix, guys. What if we were to instead write all of these numbers down? Why is this considerably harder to crack? Big numbers, number one. Number two, negative numbers. And number three, wait a minute. Which one maps to be E? This one, and then let's see, 1, 2, 3, 4, 5, 6, 7. This one. Question, do the same letters even end up with the same numbers? No, matrix multiplication totally messes that message up. Now, it's a totally messed up message until, how do we decode that message? We encode it with A times the message. How do we decode?
Inverse.
Yep, we need to add one more piece of notes. Nice thing is, remember your calculator can find inverse, right? We decode by taking A times B is the result. A inverse, which the nice thing is our calculator can do for us. We don't have to necessarily solve it by hand. By the encoded matrix. Let's say coded based on what they used. By the coded matrix. So if you multiply the inverse by the coded, it's kind of like you are multiplying A by A inverse, and whatever A did in being multiplied, A inverse will undo, and guess what you're going to go right back to? The original. Luke, what's your question, bud?
I understand that those insights here are supposed to be the same, but wouldn't it be B times A, since you have to multiply the top 3 of B times the vertical 3 of A? If it would be A times B, multiply the top 3 by the vertical 3.
Oh, I must have done it in my calculator backwards last year. What's Luke saying?
That's true. Then you gotta have the.
If we go cross and then
you gotta
down,
have
are those
the
gonna match?
greater row first.
Now, hold on, who can figure out the mistakes? I made it look really good. I totally made it work, but why? Oh, come on, it's an easy mistake. What was the mistake I made?
You gotta do
You use
row.
the. Holy whoa. Oh, it's 5 then.
Oh, not 3 by 3.
Oh.
Struggle. We need to switch it all then, huh? Doesn't ruin everything. We're just going to change them. I must have put in my calculator last year the message in A instead of B. Struggle. So now we have our correct order 5 by 3, and then we have 3 by 3, and then now those two legally match. So we have our message by our encoder. So we need to go ahead and change this just for what we defined. Sorry, let me go ahead and make sure you guys can see that. Good catch, bud. Good catch. And say if you put it in your calculator correctly, which I guess I didn't do last year, I did it backwards, then we would end up with B times A. Aren't there little brackets or something around matrices in your calculator? There we go. Nice thing is, that's the only legal way to do it anyway, huh? That's the only legal way to do it anyway. So then, hey, if we switch the order, remember, matrix multiplication cannot go both ways, right?
And those are gonna let us use calculator, right?
Yeah, oh definitely.
Okay.
So we need to go ahead and take our coded times. If we switch the order up above, we switch the order down below. The coded times AN first. Now you guys have your calculators out, right? We're going to do one example just because these take time, and then we'll see how you guys do on homework 2 tomorrow. Let's see if we can do one. Ready? Encode the following message. I've already given you the numbers. Wait, why did I split them up by 2s?
You have a 2 by 2.
I have a 2 by 2. I have to split them up in 2s. Encode the following message. And check by decoding. This is all calculator work.
Okay.
Help is on the way. So how did I get my message? I said H, and I looked at my little key from above. H goes with 8, E goes with 5, L goes with 12. I took all my letters, I made them numbers. Every space I made a 0. Every space I made a 0.
Very nice.
Based on what we wrote near the page, does it make sense? Ooh, it disappeared. Does it make sense? This is what we're going to have our calculator do. We're going to take our message, we're going to make a nice long matrix with lots of rows. Technically 1, 2, 3, 4, 5, 6, 7, 8, 9. We're going to have a 9 by 2 multiplied by a 2 by 2. Is that legal? Yeah, it is. So it's the message times the encoder. What's our calculator going to give us?
Not very useful numbers. Negative 34.
Right? Very tricky numbers, all mixed up. A coded set. Now, how are we going to check by decoding?
use the results.
We would take our coded, what would we multiply by?
Inverse of A.
Inverse of A. How do we do inverse in our graphing calculator? What button are we gonna hit? Remember, we can do the -1, we can
That's
cheat.
inverse.
No, and you can make it with matrices, otherwise it won't understand. But then what's gonna happen after we do this weird mixed up coded message times the inverse is gonna come right back to
The 9/2
something someone can very quickly decipher using A is 1, B is 2, C is 3. Now guys, in homework, you don't have a lot of these, but you do have a few that say, hey, here's a message, you figure out how to encode it. And they give you a matrix just so we can all have the same coded message as we work on it. But they might also say, hey, guess what? Here's this random jumbled mixed up message that's been encoded by this guy, decoded to figure out what the message says.
Decode you got the coded one, and the inverse of the 2/2 one. So you're gonna decode coded.
So we would make this matrix up here, we'd make him A. Now kiddos, for tomorrow, I'm going to have all this stuff put into my calculator, that way you can see how it works. So we have all the information written down, just like to know how to use our calculators. Class has come sadly to an end. However, tonight we'll see if you guys can encode and decode, along with things like area, collinear points, etc. Bye guys!
Let me see.